Greetings, this is Artie from Artifact Electronics. Today we're going to talk about a solution to a problem that I've been running into. And if you're into repairing vintage electronics, I'm sure you will encounter it if you haven't already. And that is, you go ahead and you troubleshoot a board. What we're looking at here is an Atari Pinball board from a Space Riders pinball machine. The troubleshooting, we're not going to talk about the troubleshooting, but rather I found the bad chip, or a bad chip, and it turned out that the chip is obsolete, has been obsolete for a while. There's no direct replacement for it. I mean, you can still find them on eBay, but you need to pay $10 for a TTL chip, plus $8 shipping, handling, and privilege tax, or however they come up with their shipping and handling charges. And the chip I found that was bad on this board seems to go bad pretty often. I have several of these boards, and last night I ran into the fifth bad chip I had. So let's see what we can do about that. The specific problem on this board is that it won't read any switches. It boots up, it works, it does everything it's supposed to, except you cannot give it any switch inputs whatsoever. So in order to find that, even though we're not going to go into detail, I'll briefly show you how the switches work and which part is the problem. So Atari used a rather archaic way to read switches, in that it basically has a memory address, a read address for every individual switch. Everybody else uses a switch matrix, which reduces the parts count and actually decreases the scanning time required. But I guess because Atari at this time, and these machines are from the early 70s, I guess they were building arcade machines mostly, and arcade machines have, 5 or 6 switches? 2 coin switches, a start game switch, and maybe 2 controllers, and maybe a joystick with 4 switches on it, under 10, so those switches were always read directly. Now all of a sudden you have a pinball machine that has, looking at this schematic, we can see this is capable of reading 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 100 switches. And it has to basically do 100 individual reads to get the state of every switch. But the way this works is that these chips generate a low for a corresponding address, for every address, and that basically activates the switch or queries the switch to see whether it's closed, and if it's closed, puts the value on a common line. And since the processor knows which address it hits, if a true value comes back, it knows that that switch is closed. It still has to do switch debouncing and all that good stuff, but that's being done in software. So we have this big huge array here of selectors over here that generate all the individual strobes for each switch possible. And it's driven by a BCD decoder over here that pretty much selects one of these strobe generators, and then the lower 3 bits of the address tells you which one of the strobes to activate. So it wasn't that difficult to poke around with a logic probe, but it turns out that this chip was bad. It wasn't outputting anything, and so no strobes are ever being generated, so no switch closures can be detected. So again, poking around, this guy was bad. It's a Fairchild 9301 BCD decoder. And what does that mean? That means you take a BCD number, a binary coded decimal, and stick it into the address lines A0, A1, A2, and A3. And if that number is between 0 and 9, one of the 10 outputs will go low, indicating what was input. If the input is greater than 9, obviously with 4 bits we can go from 0 to 15. So if the input is 10 to 15, that's an invalid input, and none of the outputs go low. Basically, it deactivates. So again, this is the part over here that selects which one of these strobe generators to activate. But yes, this guy was bad. Now, the 9300 series of TTL was used quite often. There are several chips used on the Atari board. But it turns out that those have direct 74 series TTL replacements, so it's not a big deal. Of course, this chip does not have a direct replacement. I had to dig around, and what I found was a functional replacement for it, i.e. something that has 4 address inputs and 10 strobe outputs or decoder outputs, one of which goes low if the input is a valid BCD number. And if we look at the data sheet, it is actually 100% functionally compatible. We look at this guy, it's got the address inputs A, B, C, D, and then the selector outputs 0 through 9. But if we look at them next to each other, we can see that the pinouts are completely different. So you have to kind of wire up some monster thing with wire wrap wire and hot glue and stuff and put it in there to make this chip work. This chip's available. I mean, Mauser has thousands of them in stock and sells them for under $1, so I'm assuming they're still in production. The through-hole part, of course. But having to make one of these, hand building one of those for every time the chip goes bad, didn't seem like a very palatable thing to me. So of course the solution is make a PCB for it. We start out by making a schematic that, if you just looked at it as a schematic, doesn't make any sense, because we've got all the outputs hooked together and all that sort of stuff in here. But really what we're trying to do is just make a board that reroutes the signals coming into the board so that the pinout of the 9301 is converted to the pinout of a 7442. And if we do that, then we'll have a board that we can put a 7442 in, which is commonly available, and then stick that whole conglomeration into the board, and we're done. So we basically, all the schematic says is all of the pins from the 9301 are connected to another pin on the 7442, performing the conversion function to rerouting all of the signals. We do it with all the logic signals and also with the power connections over here. The power connections are actually the only thing that match on the pinout, but that's basically what the nonsensical schematic looks like. And then we get to the next step, where we make a layout. So we make a board where this is the 9301 side, and this is the part that gets inserted into the board, this column and this column of pins. And then on the left side, which is labeled 7442, we put in a socket or the actual 7442 chip, and voila, we got a chip replacement that is slightly bigger than just a chip, but it works just fine. Unfortunately, I messed up on this, as you'll see in a minute, and I assigned the wrong layer to the legends, and so the boards came without any writing on them. But here are the boards. So here's one of the boards. Had these made in China, and as I mentioned before, none of this writing is on here. But that's because I guess the board house, the layer that I had these that I had the text on is a layer that the board house doesn't use, and since I made these in a rush, I forgot to check, and so we have a board without any instructions on it. The reason I rushed on this, by the way, I was doing a bigger project, and getting like 10 of these boards made costs $5. The problem is if you only order these boards, you pay $5 for the boards and $28 for a DHL delivery. So I was doing a bigger project, I was going to pay the shipping charge anyway, so I kind of cranked this board out in a matter of an hour or so, and once the boards came in, noticed the error, but it's only cosmetic because the board actually works. So how do we stuff this board, or how do we use this board? So let's look at an assembled one. And here's what an assembled board looks like. We essentially have pins that come off of a strip of pins like this that go into the 9301 socket. So the part that was labeled 9301 on the board has those pins so it will fit into the board. Let's see, do I have the orientation right? Yes. This part goes into the 9301 socket. Then I have the 7442 over here, and it's socketed for two reasons. First reason is that if this ever goes bad, you can easily remove it. Second reason is that when you put these pins underneath, they do stick up quite a bit, and you can't really solder the chip directly to the board. I mean, I'm sure you could use a different kind of pin if you wanted to solder the chip or trim these or whatever, but this is the first prototype I put together, and so let's try it out and see if the switches start to work again. Here's a bad guy. If I can get him out. Come on. And come on. F9301 made by Fairchild, and he don't work. So now we take our new device and plug it into the board. I know this is kind of ridiculous because we got a socket down here, and then we got a socket here and all of that. Theoretically, you could, not theoretically, this is probably what I'll do, is I won't be putting a socket on the board itself, but rather soldering this whole thing in directly, which will lower the profile a little bit. And since this is socketed already, if there's ever anything wrong, no problem. You just have to watch out. It has these rather huge bypass capacitors here. There's one behind it, even though there's a lot of clearance, but push comes to shove, if there's any capacitors in the way, remove the capacitor and put one of these in its place, and they lay flat. And this is pretty solid over here. I mean, I can lift the board with it. It doesn't move. It doesn't need any extra support. There's no room for any extra support. But let's see now if this actually works. So I'm in the process of building a bench test setup for these Atari boards, because if you've seen any of my previous episodes on the Atari machines, I do have a few of these boards in various states of disrepair, and it's kind of difficult to have to put them into an actual pinball machine, plug everything in, and then lean into it and stick your logic probe or scope on things, and then you find something's wrong. You have to disconnect it, take it out, put it on the bench. So I'm in the process of building a few extra things so I can fully bench test these boards without having to, actually put them inside a machine. And I haven't gotten very far yet, but the first thing I did was I built a display. The original displays are the gas discharge displays in the machine that take plus minus 90 volts. And I mean, if I wanted to have an actual display, I would have to get a transformer, get an auxiliary power driver. It seemed to be too much of an effort, so I built this thing, which emulates or simulates an actual display perfectly. Except, of course, for the voltages, but that's functionally, it does the same thing. So, for our test, let's power it up. The board is simply powered by a benchtop supply, which goes in here, and it just feeds the 5-volt regulator. On the machines themselves, the input voltage is kind of high. It's about 12 or 13 volts DC, unregulated, which does generate a lot of heat. Now, I run this guy at 8 volts, and there's a noticeable difference, or noticeable change in how hot all of these parts get. So that's probably another thing I'll be looking at in the future, how I can reduce the raw DC input to this board inside a machine to something around 8 volts, which is more than enough to drive the regulator. But other than that, the display plugs directly in, no modifications required to the board. The only mod I have right now is I run a 5-volt line from the display to the board, because these displays, all this logic works off of 5 volts. And what they do on the original is they take the plus 90 volt supply and with a Zener diode bring it down to 5 volts. I guess for plug compatibility I could add that to here, but that makes me a little bit queasy. So for now, I'm just going to run it off 5 volts. So let's power this thing on. So this is actually what the pinball machine does when you first turn it on. It lights up all of the segments and goes through the player indicators, player 1, 2, 3, and 4, and sits there. And after a while, I guess this blanks out, and then when you play, and it shows you the score. But this is a great way on the bench to see, is the machine working? So what I did before is, one thing they did, there's a test switch inside the coin door, and if you hit that test switch, it starts going into lamp tests, solenoid tests, and switch tests. And what they did as a convenience, actually, is that one of these dip switches emulates the test switch in the coin door. And when you press it, the display should change, which before, when we had the defective 9301 in here, no matter what I pressed, I even tried giving it fake switch inputs. This is where the switches come in, by the way, giving it fake switch inputs and stuff, and nothing worked. And that's, of course, when I diagnosed it and saw that it was never generating the switch strobes, which this should be doing right now. So now the test is, if I hit this dip switch, it just went off. That is normal. They do that to save the displays, because the original the gas discharge displays will burn out if they're left on 24/7. Remember, they're being fed by 200 volts total. But anyway, if I hit this switch, it should go into test mode 1, and there you go. It now it's showing us the replay scores, and it's saying it's in test 1, which is, I think, the lamp test. We can't see anything because I haven't built that yet. I need to build a board that, again, will use LEDs, plug into here and here, and basically have an LED per lamp. And when we're in lamp test, they should all light up. The next test I have to simulate a press of the start game button. That also didn't work, of course, but when I hit it, come on. Oh, sorry, wrong machine. On this machine, which is a Time 2000, I have to toggle the test switch again. And it jumped to test 2. Test 2 pulses the solenoids. I'm not sure, it either pulses the solenoids or reads the switches. But then there's one more test, and again, and it should go to 3 on the bottom. And there you go. So now it's in, I think now it's in the switch test. I don't know, we'll do, once I've built the extra boards, I also have to build a board that has little push button switches on it, simulating each of the switches, and another light panel that shows when the solenoids are firing. So you can see a light up indicating that a solenoid's firing. Now keep in mind this is all working under low voltage. There's no real solenoid voltages, real lamp voltages or anything like that in there, but I'm just checking the logic here. And if it works on the bench and it still doesn't work on the machine, then there's usually power supply problems that fail to deliver the proper voltages required. So now if I press the test button again, it should exit the test mode and go back to the attract mode. So toggle it on and off, and there you go. Well, I hope you can draw some inspiration from this video on how to overcome a lack of parts availability. This doesn't always work. You won't always get away with just a single tiny board. You may have to put more than one chip on it to simulate, what it's replacing. But the bottom line is you can pretty much simulate anything. I mean, you can start putting surface mount parts on top of this board and reduce the profile even further, and lots of things you can do with this. But there's always, where there's a will, there's a way. So thanks for watching. Please like, subscribe, and leave me a comment. And we'll see you next time.